Welcome to today's lesson. This is a review tutorial. We will be reviewing arithmetic and geometric patterns. So we are in review mode. It is section 12.1 through 12.4 in our textbook. When I gave you this note sheet, I asked you to try all 8 of these first. So you should already have tried these before watching this tutorial. If you have not already done so, I'd like you to pause and try each of these. Let's look at the directions. It says to label each either as arithmetic, geometric, or neither. If it is arithmetic, I'd like you to state the common difference D. If it is geometric, I'd like you to state the common ratio R. And I'll just tell you a hint right now, especially if you have not already done so, that neither is actually just a distractor. Each one of these 8 patterns is arithmetic or geometric. None of them are neither. So again, if you have not already tried this, why don't you pause right now and spend 5-10 minutes trying to figure out which ones of these are arithmetic and which are geometric. Pause now, please. So I hope that you've already tried these. When we're looking for arithmetic, we're looking for a pattern where we are adding to get from term to term. When we are looking for geometric, we are looking to multiply to get from term to term. Those are our arithmetic and geometric patterns. So let's do the arithmetic in red. Let's look at A. We're going from -8 to -3 to +2 to +7 to +12. Looks like we're adding the same number, and in fact we are. This is arithmetic, and D is equal to 5. We are adding 5 to get from one term to the next. Let's look at B. We're going from a squared to a cubed to a to the 4th to a to the 5th to a to the 6th. Obviously, there's a pattern. Now, I understand that the pattern in my exponents looks like I'm adding 1. I get that. But this is not an arithmetic pattern because we're not talking about the exponents. We're talking about a squared turning into a cubed. How does a squared turn into a cubed? It looks like we have to multiply by a. And then a cubed times another a would become a to the 4th, and so on and so forth. We are multiplying to get from one term to the next, so this is geometric, therefore it has a common ratio, and in this case, the common ratio is a. When our exponents are changing, that must have happened from multiplication, so this is geometric. As opposed to part C, where we're going from 1a to 2a to 3a to 4a to 5a, now all we're doing is adding a, and then adding another a. That's going to change my coefficients. I am adding, so this is arithmetic, and my common difference is also is a. Let's look at part D. We're going from 5 to 4 to 3 to 2 to 1. It looks like we are subtracting 1, but that is not what we're doing. We are either adding or we are multiplying. So we must be adding a -1. Adding a -1. This is arithmetic, and our D is a -1. That's when the D is negative, we're going to have a decreasing sequence. This is a series, I guess, because we are adding all of the terms together. So this is a decreasing series, arithmetic. E, -27 to 9 to -3 to 1 to -1/3. Well, one thing I notice is that my terms are alternating, and that cannot happen for an arithmetic pattern. And since I said that each of these are either arithmetic or geometric, this must be geometric. Let's see if we can figure out what R is. R is the number that we're multiplying to get from term to term. Some people see this pretty easily. If you have any trouble discovering what R is, you can take any two consecutive terms and divide backwards. So I could take the 1 and divide by -3 to realize that my R is -1/3. Or I could do 9 divided by -27. Any two consecutive terms divided backwards will give you what R is. So that's what we must be multiplying. I knew we were multiplying by a negative because a negative R is going to alternate my terms from positive to negative. Let's look at F. 0.555555555. Now, I understand that this is actually just one number, but I'm talking about the individual pieces of this number. If you look at just this first decimal, that is 5/10. And if you look at the next decimal, that just this second 5 represents 5/100ths. And if you look at the third decimal, just the third 5, that is 5/1000ths. And you can see what's happening here. If this kept going on, we would be adding 5/10ths plus 5/100ths plus 5/1000ths plus 5/10,000ths, and this is a geometric series because we are multiplying by the same number to get from this term to the next term to the next term. The numerators are not changing, so we must be multiplying the numerator by 1. The denominators are being multiplied by 10 because we keep increasing a 0. So this is a geometric series, and we are multiplying by 1/10. And then my final two problems are sigma notations, and I want you to understand which one is arithmetic and which one is geometric. The clue that we've been talking about to notice that it's arithmetic is if there is a coefficient, a number multiplied to n. Since this is a coefficient, this is going to be an arithmetic pattern. And if it's arithmetic, we have a common difference, and that coefficient is what the common difference is. You do not need to find all of the terms of this series to discover that it is an arithmetic pattern. You just need to notice that it is a coefficient multiplied to your variable. And that coefficient will be that common difference. As opposed to our final problem, which is our sigma notation, when you see a base is the number being raised to an exponent. When you see a base, that must be geometric. And if it's geometric, there is a common ratio, and that base is the common ratio. So in this case, R is 7. Again, you don't need to find all of the terms to discover that this is a geometric pattern. So thanks for watching this. This is just a quick review of a bunch of things. There are a bunch of formulas that we're going to be using, and we'll be doing those review problems in class. Thanks for watching this, and I hope that you got all 8 correct. We'll see you in class. Bye-bye.